important. Having a good understanding of why things work the way they do, that's important. And also, I call this a motivational type problem because most people, after they look at this, they don't want to do it again. I don't want to do a ton of problems like this. It's terrible. So if only there was a quicker, easier way to do it. Well, guess what? There is. And now you're really motivated to learn what that is. Right? So, you know, an old teacher strategy, show the way that I could make you do it, and then tell you I'm not going to make you do it that way. And this is how great I am. I'm only going to make you do it the easy way. Right? Now, the median and the mode. Well, the mode, we can't really find the mode the way we were before. What we can find is what we call the modal interval. So I'm going to make a note of that off on the side here. Mode of a frequency table. We call that the modal, M-O-D-A-L, interval. Right? And this is something that you only really start to think about, or you only start to consider when you think about the data. All right? So, and again, the theory of it. And I know there's many of us that are like, just show us how to do it, man. Like, I know, but like we want to understand why things work the way they do. So the modal interval is the interval that contains the most values, right? So off the bat, you want an answer? I'll give you an answer. It's the 50 to 59 interval. And that's because it has the most values. Right? But we can't say that it's the mode because the mode is defined as the most common value. Right? How can an interval be a most common value? It's not a single value. So it defies the definition of mode, right? So we need a new term, and that's where modal interval comes from, right? Also, just because the most values are between 50 and 59 doesn't mean that the most common number is between 50 and 59, right? So for example, let's say in the 10 to 19 range, every one of those 51 values was the number 11. Right, so we have an interval of values from 10 to 19. All of them are 11 though. All right, cool. In the 50 to 59 range, maybe 10 of the values are 50, 9 of the values are 51, 8 of the values are 52, 17 of the values are 53, 12 of the values are 54, and so on until we get to a total of 92 values in that interval. We're never going to get even close to 51 of any particular number, but the interval itself contains the most values overall, right? So there's a difference between the two. In this context, we're more interested in the interval that contains the most values because we got to imagine that there's some reason for why we set up the intervals this way. Maybe it's there. Maybe we're talking about ages. Yeah, maybe we're talking about demographics. Maybe it's like TV viewership. You know, like what's the most or what age group finds this type of show the most appealing? You know, and so like let's say you have some sci-fi show, for example. Maybe the young ones like it, the 20-somethings, the 30-somethings, not so much. The 40-somethings, but then the 50-somethings really like it, right? So what kind of advertisement are you going to put on during those shows? Like if you're going to do product placement within that show, are you going to like will your product placement be a can of Bud Light, or will it be a can of like or a container of fiber? You know, like what are we looking at? Like what should we be focusing on if we're advertising? Right? This kind of distribution of data could really tell us a lot. Right? So very, very important. But if it turns out that every one of the individuals in the 10 to 19 range was 14 years old, that's not going to make much of a difference compared to, 11 50-year-olds, 20 51-year-olds, and so on. Right? So it doesn't add much meaning to the whole process. Now, as the median concept is kind of a pain, all right? So what I want to do is just kind of look at Desmos exclusively for a second, and show you how this kind of works. We'll talk about some of the nuts and bolts of Desmos real quick, all right? And maybe not so real quick. So actually, let me pause this recording. All right, resume recording. So you're in GeoGebra. You're under GeoGebra. Jeez, wrong class. You're in Blackboard. You're under announcements. One of the little tabs on the side here is learning resources. I probably should come up with a better name for that. There's a few things that I tucked away in here. One of them is the NetTutor online tutoring. That's something to be mindful of, because if you need tutorial services, a little extra help from the tutoring center, there's no physical place to go. So this would be an avenue that you could pursue. But I also have a folder here that contains Desmos tutorials and applets, right? So I didn't want to just hand wave my way through any Desmos related stuff. So what I did was I just kind of curated this and walked through a few different things, like creating a pie chart, like specific graphs, which we're going to talk about later. But the tutorials are really where the magic happens, right? So one of them is, if you look at the list, computing statistics with Desmos. It's just a 2-minute video. And so I'm going to take a second and play that now. But let me stop the share real quick, because I'm not confident that I put the audio on. Computer sound, I need that. All right, so let's watch this video together real quick, and then I'll talk about it and walk you through the process. All right, because this is, I don't want to say it's a game changer. I don't want to be over dramatic about it, but it's got some good talking points. All right, so let me pop this up.
So this time we're going to take a look at how to use Desmos, the online graphing calculator, to do some basic statistical calculations, just like I showed you in the previous video in Excel. So I took that same Derek Jeter number of hits data, and I've actually entered it into Desmos already just to save some time. But just to show you how I would have done this, we just click into one of these new cells here, hit the little plus sign, say we want to insert a table. Now, since I only have one variable data here, not two variable data, I don't really need this Y2 column at all. I need to work with the X2 column. And by the way, the only reason these are called X2 and Y2 is because I have another table up above that's called X1 and Y1. It just doesn't reuse the same variable name. And I want to delete these values that are in there already. And I would just go ahead and start typing in whatever numbers I needed to type in. Whatever my data set was. So I go down through and enter all those values, and that's what I've done here. You can see I've got the values all entered and ready to go. So again, I'm going to click in the next cell, and I want to use one of the functions. So over on the bottom right here, I'm going to click on the functions button, and I've got trigonometric functions, statistical functions, and some miscellaneous stuff. Well, if you just take a look around here, you can see that we're going to find the things we need. We could add them all together. This length function is not something we're interested in right now. The mean is what we're interested in. The median, I could use min and max to find the range. Here's my population standard deviation, which is typically not what we're going to use unless we're entering every value from a population. But usually what we're dealing with is a sample standard deviation, which is this guy right here. The quantile is kind of like a quartile, but again, it uses the same method as Excel. It uses the percentile method, so we're not really interested in that right now either. Some of these other functions we'll get to later on in the course. But let's go ahead and find the mean. I'm just going to type in mean, and I'm going to say x1. Just type x followed by 1, and you can see it's already calculated the mean. If I wanted to find the median, I'll just type median. Notice you don't need to type the equal sign here like we did in Excel. And I just simply type in x followed by a 1, and it figures out that I mean x1. So when I do type the equal sign, Desmos actually says, I don't really understand that. So that's your indication that we don't actually need the median or the equal sign to type these functions. If I wanted to find the range, I could do max x1 minus min x1, and there we go, there's my range. So real quick, using some of these other functions in Desmos, hope that helps.
I don't want it anymore. So let me stop the share. So a little something there. You know, it's got a little tutorial. There's, you know, a few more like that, but this is the kind of thing that'll, you know, it'll be kind of like your go-to. And I'll be putting up more video tutorials. I'll make my own too. That was some other dude. So yeah, just something to consider, because if I wanted to find a median, I could do it as a frequency table, and that would be the way to go. You know, so it's just, you know, it's a technique question. It's in navigating the functionality of Desmos. And so I just realized that I haven't screen mirrored yet, so I don't know why I'm typing anything. So share, bring it back. YouTube video within a YouTube video. That's going to be something, right? So I have the whole screen up here, but I really don't need the whole screen. I needed to be able to see the plus sign here, right? So that plus sign is where you find all those extra functions that he was talking about, and you can see you could pop in an image. In Desmos, it's kind of cool. I mean, that's beyond the scope of what we're going to do right now, but it's kind of cool because what you could do is put an image into the graph, like a picture, and you can start playing around with different ways in which you can model that picture using math equations. But that's beyond the scope of what we're going to do. Table is what we want, and it's defaulted to x1, y1, right? So I got it's kind of out of order here, so I got all these extra things that I don't really need, so I'm just going to get rid of them, and I'll bring back the notes.
Quick question.
Sure.
Are we doing this to find the mode?
We're doing this to find the median.
Okay.
Right, and it's really so that we don't have to use that nasty cancellation technique from last time. I mean, so you know, it's kind of like a trade-off.
Okay.
So 14.5, 24.5. So we put in the calculated values for the class midpoints: 34.5. 44.5 and 54.5. Then 51, 13, 22, 4, and 92. All right. So we have the table in. As far as points being plotted a graph, we don't really need that. And in fact, there's other ways you can do this on Desmos where the graph wouldn't show up. But I figure let's just keep it in the graph display, even in cases where we don't really need the graph, because it's just better off for us. All right. So what we're going to do first, I guess, it might not be the worst idea in the world to verify that we got the mean right. And we did all that work, so let's take a look. So function stat will find the mean. We want the x1. So we're literally typing, just as he said, x1. How did it know it was going to be a subscript? Well, it's just referring back to everything else that happened in Desmos. It knows that the only other time that I ever referenced an x, it had a subscript of 1, so that must be what I'm talking about, all right? But I also have a y1 column, so that needs to be accounted for. So I'm going to type in comma, and then y1, and then hit enter. And then it doesn't work. Why did that not work? Is mine jammed up here? I'm just trying this real quick to see if maybe I screwed something up. No, that should work. No, it's not in there. All right, well, let me just pause. It is what it is. Sorry about that.
Take
So,
the comma out.
what?
Take the comma out.
Take the comma, it works without the comma?
Try that.
X1, Y1. Well, it gives a number, so that's something, but it looks like it's finding the average of the product between the two numbers. Definitely not 38.511. You know what? Rather than waste everybody's time anymore, what I'll do is I'll just make a note that we're coming back to the median on this.
Is using the Desmos calculator the same as using the TI-84 graphing calculator?
No, it's different. The reason why we're using it is because it's free. You know, so
But
that,
you can still use the TI-84 to do all this, right?
oh yeah, if you're comfortable with TI-84, that's fine. It's just I'm going for a completely free approach to education these days, and so I'm trying to make that work.
Right.
So there's going to be hiccups and bumps along the way, and this looks like the first one. So, like I said, we'll come back to this. We'll find the median later on. Not tonight because I'm looking at the clock and I don't want to waste time. And also, I got to research it. I got to figure it out. So for now, we'll move on to measures of variation. This is straightforward enough that we wouldn't need to be beholden to the Desmos calculator for anything. But I mean, we'll run into the same problem when it comes to the frequency table, but we'll cross that bridge also. But number one, for measures of variation, we're going to look at the same way anyway, where we'll do it by hand, and then we'll talk about the technological approach to it. All right. So, what a measure of variation is it's a number, specifically just a number that talks about how spread out the data is or are. Right. So, that's very uncomfortable to a lot of people because it's like, well, is it a big number or a small number? And my answer to that is it depends, because if you get a standard deviation and that standard deviation is 127, that number is almost meaningless until you have something to compare it to. All right. If the standard deviation is equal to 0, then you know that there is no spread to the data. So that there's meaning and value to that kind of scenario also, but it's not going to tell you anything more than that. All right. We already knew that the data was spread out in some capacity because the numbers are different from one another. All right. So I know that this standard deviation, just by looking at it, is going to be something other than 0, because the numbers in example 1 are 2, 3, 6, 3, 6, 8, and 0. Right? They're not all the same. They're different from one another. All right. So what I want to do is come up with a standard deviation for one data set and then use that as a point or a value of comparison for another data set. Right? But since we're working on the skills right now, one thing at a time, let's learn how to find the standard deviation of just a simple set of data. All right, so we have this X list of data. I organized it horizontally because it fits better, it looks nicer. But what we want to do really is look at this formula here. I'm going to highlight it. The X minus X bar squared over N minus 1. Right, X minus X bar squared over N minus 1 will give us what's known as the sample variance, S squared. Now, S itself is the standard deviation. So once I find the sample variance, all I have to do is take the square root of it, and I'll have the sample standard deviation. All right. Now I'm calling this a sample, but I haven't applied any context to it, so we don't really know. But it's a set of numbers, and it's not all numbers from negative infinity to infinity. So there's a reasonable assumption that it would be a sample of data. We just don't know what it has to do with. Are these ounces of water in a bottle, or something else? We don't know, right? But if you look at the formula, you could see that there's an x. All right, we got x. All right, so we're good there. There's an x bar, so we'll need that. And then there's an n. Everything else is some kind of operation based off of those values. So what I'm going to do is first find the mean. I'm going to find the x bar. All right. So we could do that in the calculator, any calculator, doesn't matter. Find the mean of the values 2, 3, 6, 3, 6, 8, and 0. And that mean is an even 4. All right. So we have that. I wanted to copy it for later, but I'll just retype it. All right, so the x bar is 4. What we're going to do is create a row that contains just the x bar values, x bar value, but we're going to write it multiple times. For each x value, we're going to create a corresponding x bar. So the number 4 is going to be written a total of 7 times.
Wait, I definitely missed how you got there. Why is 4 written 7 times again?
Because for each one of the x values, we're going to write the x bar value. Because from each x value, we have to subtract the x bar value of 4.
Mm-hmm.
And so it makes sense to just list for every one of those x values a 4 along with the x value. Because in the next step, we're going to say x minus x bar. So we're going to find the result of each one of these computations. Or we'll compute each one of these just to keep it simple. All right, so we'll have a -2, a -1, a 2, a -1, a 2, a 4, and a -4. All right, so these are all my x minus x bar values. I'm going to create a line here to keep it somewhat organized. All right. So we have all those entries. Following order of operations, if you really think back, like PEMDAS from computational skills, college algebra, whatever, we start off with parentheses. We've already taken care of that. Next up is exponents. All right. So I'm going to take my x minus x bar, and I'm going to take each one of those values and raise it to the second power. All right. So I'm going to take the -2 and square it. Now, when you take a -2 and square, you got to be careful. So if I do -2 squared, it's going to give me -4. That's incorrect. Based on what I wrote here, you're telling the calculator, and this is whether it's a TI-84, scientific calculator, it doesn't matter. You're telling the calculator to, by order of operations, to take a -1 and multiply it by 2 squared. Right? That's what you're telling the calculator to do. Whether that's what you intended is a different story. What you need to do whenever you raise a value, specifically a negative value to a power, you want to get that negative value in parentheses. That's assuming that you don't want to just recognize, oh wait, if I ever square a negative, it's always going to be positive. So I could just disregard the negative. All right, so this is going to become a 4. Do the same thing with a -1. And you know, the ones that are positive, those should be easy. Those should be easy enough. You take 2 squared, you get a 4. Negative 1 we already did. Positive 1. Again, 2 squared is 4. 4 squared is 16. But then maybe you look at something like the negative 4 squared, also 16. All right, you see how the 2 negatives, or the negative 1 squared gives you a positive. So what we want to do, if you look at that numerator, it says find the sum, right? So you start saying, okay, well, what's the sum really talking about? It's the sum of this row, right? So it's just an organizational strategy. I'm just going to get rid of that a little bit. And I'm going to get a little cute with this. I'm going to tuck in an equal sign, slap in a summation symbol here, and write plus signs all across the way. Right. Then it's just a matter of actually performing the addition, whether you do it in the calculator or by hand is your business. But we got 14, 30, 46 total. Right. So one way or another, you should come up with that 46. Right. So that's the top of the fraction. The top of the fraction has been accounted for, so that's good news. Now we need the bottom of the fraction. Bottom of the fraction is n minus 1. N is the total number of values on the set. So I'm just building around all the work that I've done. I'm going to go green for those who can score home. N minus 1. So I'm going to take this whole shabiggity bangity boom here, and consequently this one, and divide it by the number of values in the set. 1, 2, 3, 4, 5, 6, 7 values. So therefore, n is equal to 7. So I'm looking at 7 minus 1. 7 minus 1 is 6. All right, all of that, if you look at what we just constructed here from this table, we just found, now it's in fraction form, but we just found the sample variance, S squared. All right. So, I mean, if I want the decimal value, 46 over 6, I can do that. 7.6 repeated. That's fine, but we're not done because the question said find the sample standard deviation, right? Sample standard deviation is equal to S, which is going to be the square root of the S squared that we just came up with. So this is my S squared, which in turn is this, all right? So this S squared, I'm going to jot down here, S squared, is going to be replaced with the 46 over 6. All right. So instead of having a decimal there, rounding that, then taking the square root and introducing what could be an unacceptable amount of error into the computations, what I could do is keep it in the fraction form, simplified or unsimplified, it doesn't make a difference, and then just pop it all in at the end. So I have a radical symbol, 46 divided by 6. Now I have the decimal equivalent, which I can round appropriately, and now I have an acceptable amount of error in the rounding because I only did the rounding once, right, in the final step. So about, so a squiggly equal sign means about or approximately 2.769. And you don't have to use the squiggly equal sign if you don't want, but it's a nice nice form of notation. All right, so that's how you'd find the standard deviation by hand. Now, granted, I mean, it's a pretty arduous process. You look at it, and I'll even call this one a motivation type problem. But it gets at what's happening, even if you don't really think about it, because, you know, like, well, a lot of times we just follow the steps. We don't think about why the steps exist. So the term standard deviation. So somewhere along the lines, we're standardizing all of this. Right? We're coming up with a standard approach. All right. Well, that makes sense. If I want to compare multiple data sets, I want to have a level playing field. So I want to have a standard way of relating the two data sets. All right. So that's fine. The deviation part, deviation or displacement, could also be thought of as subtraction. So how far one thing is away from something else, right? That's what we would think of as a deviation, right? Well, with that in mind, we're looking at that subtraction step as being the deviation part of the standard deviation, all right? So then the only question that would come out of this would be, well, all right, well then, well, two questions really. Why do we square it? And what's the whole deal with the n minus one? The n minus one I can't answer yet because that's part of another unit down the line. We got to learn a bunch of things before we can even hope to understand that one. But the squaring part is to get negative values to become positive. That's why we square and then square root later on. All right. Now, why we can't just drop the negatives? That there's a little quirkiness to that, but the short answer is it has really everything to do with the fact that a lot of the probability concepts that exist are based off of the concept of standard deviation. So somewhere along the lines, somebody made a decision, much like how we measure things in feet and miles. Somebody got to make the call and we're stuck with it. And everything was built based off of this basic infrastructure, right? So that's where we're at. We're stuck with this concept of standard deviation because somebody said, you know what, let's square it to get rid of the negatives rather than finding the absolute value to just get rid of the negatives instead. And so there's different schools of thought, but that's a little bit of the rationale behind it. But the number itself, 2.769, it just tells us that there's some spread, but we already knew that. It isn't until we compare it to another data set where we could start saying, all right, this is more spread out, this is less spread out. And then what are the characteristics of a more spread out, less spread out data set? That's part of the conversations that we're going to have moving forward. Now, in terms of doing this on the calculator, this part is a simple data set. So this will work. All you have to do, functions, stats, you want standard deviation. You see that there's two options there. You have the standard deviation, and then you have the standard deviation. I'll show you the other one. Standard deviation P. That standard deviation P is not the one that you want because that is for populations. All right, we're looking at a sample standard deviation. So the one that doesn't have a P on it is the one we want. And just like we did before, without the frequency table stuff, it's just a raw list. All right. Two, 3, 6, 3, 6, 8, 0. All right, so close parens, enter, and you can see that in terms of the actual decimal, I don't know, is it exactly the same? Yeah, it was exactly the same. If it wasn't, at least it would round to the same thing. Sometimes there's a little bit of variation in the answers, but 2.769, same deal. Now, we know, and this is TI-84, Desmos, whatever calculator you can think of, the more data you have, the more stuff you have to type in, the more difficult it's going to be. All right. It really doesn't matter because you're still dealing with physically having to get the data into the calculator. Right. But the benefit of doing this on a computer is that you have the copy paste ability of this where you can just duplicate your work and then just change standard deviations, STDev, into mean or median or whatever, and work with the same set of data and just get different outcomes. Also, and this is a big deal, and you know, people, you know, they either like this or they don't. Your Desmos work is sufficient work on a test. All right. So if I ask you to show all work for something, and you show me a printout of your Desmos, you just share a link to all your Desmos work that you saved, that's sufficient work on a unit test. All right. So just something to keep in mind. The only drawback, like I still got to figure out what the hell went wrong with the frequency tables, and once I do that, then we'll be fine. But until we get there, that's always going to be kind of hanging out in the ether. But we'll figure it all out together. All right. So I'm gonna kill the recording.